My name is Josh Snyder. Let's talk about the queues your query waits in. But I might as well have called this talk "So Much Queuing, So Little Time." I have about 58 minutes of material, but I'm pretty caffeinated, so let's see how much of it we can get through. I'm going to stop for questions at, I think, 4 points throughout the talk, so we'll definitely have time to get those in. Settled escalator etiquette in London, where this sign is, and numerous other places, says that if you're going to stand still on the escalator, stand to the right. If you're going to walk on the escalator, walk on the left. So why, oh why, did Transport for London cause major upheaval by asking people to stand still on both sides of the escalator, effectively blocking all the people who wanted to walk? This introduces us to our first two queuing theoretic concepts, latency and throughput. Latency is the amount of time required to get a traveler from the bottom of the escalator to the top. Throughput is how many travelers can take that escalator in a second or a minute or an hour. I generally think of latency as the limit as we approach the smallest sliver of work, and throughput as the limit as we approach the maximum sliver of work. So to try to understand a little bit about this, let's do some hypothetical escalator analysis. A person standing requires one stair, and then it could be a person in front of them and a person behind them. So they take up one stair of space and 24 seconds on the escalator. 24 stair seconds. A person walking requires 12 seconds. They're faster. But they take up more space. They can't be as tightly packed as the people standing. To break even, walkers have to be spaced less than or equal to 2 stairs apart. And the study found that for short escalators where numerous people might be interested in walking, they could actually achieve something along these lines. But for longer escalators, the problem was not enough people were interested in walking and they couldn't get the spacing short enough. So the interest of some people in walking up the escalator lowered the overall throughput dramatically. This link below has more details about the study. I couldn't get my hands on the actual public scientific write-up, but that link I think explains it pretty well. So what's to come in the remainder of this talk? We'll divide it up into 4 sections. The first section will cover 2 favorite tools, IOSTAT and load average. The second one will cover layers and layers of latency. And the third will cover managing multi-tenancy in applications. And the fourth will cover load balancing and unbalancing. Along the way, we'll cover a lot of queuing theoretic concepts. I find all this really fun. Hopefully you will as well. I've mostly taken out all the math, although there is plenty of fascinating math involved too. So, IOSTAT. Who here has used IOSTAT? Cool. So we have a little bit of an understanding of what it does. It presents disk I/O statistics, keyword being statistics. These are averages of disk I/O activity over a sample period. IOSTAT takes an argument saying how long you'd like those sample periods to be, and it aggregates over that period. On Linux, IOSTAT gets all of its disk information from this file called proc/diskstats. And I'm terribly sorry to users of other operating systems, but I have all Linux-specific examples. So how does IOSTAT work? Well, IOSTAT reads proc/diskstats over its sample period. Let's say it's sampled at time equals 0, and again at time equals 10. So we're running it with a 10-second interval. When it does that, it learns that, for instance, there were 476,346 reads that have been done against a given disk at a given time. Proc/diskstats just contains ascending counters of I/O activity. This next one is the number of sectors that have been read in 512-byte sectors. Doesn't matter what your disk uses, it's 512 bytes to proc/diskstats. This is the total aggregate milliseconds weighted by I/O. And this is the amount of time that the device was active. And we'll go into details, including the units, as we move on. So the first thing IOSTAT will do, and that we will do, is subtract. Take the difference between the two numbers to get what changed during that period of time. And next, normalize. It was a 10-second sample period, so we'll divide by 10. And here's some units to help you out. So we know that there were 1,676 reads per second. Multiplying by 512, we know that we did 190.83 megabytes per second of reads. We had 4.79 seconds per second of waiting by I/O and 0.9464 seconds per second of busy time. So 0.9464 directly correlates or directly indicates a 94.64% I/O utilization. And this is average queue size. We'll get into a little more about this in the future slides. So we are missing a couple more measurements that IOSTAT presents. Let's go into how those are derived. So the next measurement we'll look at is RA wait, the average time each I/O waited. Well, in aggregate, the I/Os waited 4,798 milliseconds. And we did 1,676 of them. If we just do a division, we'll see that it took 2.86 milliseconds on average per operation. Average request size is pretty similar. It's just sectors divided by reads. And here we see, oh, well, this is probably a heavily sequential workload because each read on average was doing 236 sectors per operation. If we were doing a smaller number of sectors per operation, we would see it would be a more random workload. Service time is the most interesting and possibly counterintuitive metric here. It is the percent utilization divided by the number of reads. It sort of is assuming that the disk can handle one operation at a time, which isn't true nowadays. Modern disks are pretty concurrent. For instance, SSDs that I run on my servers have peak at efficiency at about 32 megabytes per second. 32 outstanding requests. So with all of that out of the way, we can present what looks like IOSTAT. This is exactly what IOSTAT would produce for this same input. All it's done is taken util and shift the decimal point 2 spaces to the left to make a percentage. Average queue size got rounded. Pretty simple. But all of this stuff is based on just sampling the information in proc/disstats. And all of it's average. None of this tells us what information about any one I/O or whether we had a 10-second I/O. It just tells us averages about what happened during the sample period. So next up we can consider load average. Load average is a statistic calculated by the scheduler. And I think it's valuable to always think about the scheduler routines that are keeping load average up to date, because it keeps me on track for, well, how did my load average get here? So it's based on process states, which is this idea that a process could be either runnable and on a CPU, runnable and deprived of a CPU, or waiting for something. There actually isn't all that much else that processes do. So to give you an example of runnable, a runnable process would be something like this one. This infinite loop is going to be runnable for the rest of its natural life. All it does is increment a counter and stay on a CPU. The scheduler might deprive it of a CPU every now and again, or maybe more often if the system is heavily loaded, but it will be runnable. So why might a scheduler deprive a process of CPU? Well, one typical answer is there was no CPU available to put that process on. In time-sharing operating systems, processes will get kicked off for all sorts of reasons, and one of them is, oh, I don't have a CPU. Another one is you're just temporarily assigned to a CPU that has something else to do. Maybe that CPU is handling an interrupt and is running through the interrupt service routine. And then there's also the possibility of bugs in your scheduler. There's a fun paper called A Decade of Wasted Cores about edge cases in the Linux scheduler that I recommend if you're interested in this. But the cool thing about CPU starvation is that it can be measured. I can tell you on a per CPU basis up top and a per process basis down below how long processes were deprived of a CPU and they wanted one. So we can see that the CPU 0 on the VM on my laptop is depriving processes of CPU time far more than CPU 1. I think that's probably because processes get scheduled on CPU 0 more often. We can see that for this one PID, it spent 3.18 seconds wanting a CPU and not having one. And all of this is just files in proc that we can read ourselves with ascending counters in them. And the formats are all documented right down here. And if we sample those files over time, we can get graphs like this one. This is a graph of CPU starvation for Cassandra, for an entire Cassandra cluster rather, showing that in fact this cluster gets spikes of traffic on the 30 minutes past the hour. If it were sustained up there like that, maybe I would think about scaling the cluster. As it is though, the client-facing metrics are pretty good, so I'm not too worried. If you're interested in this kind of stuff, I highly recommend Brendan Gregg's book. It goes in a resource-by-resource analysis of, for CPU, for disks, for memory, what sort of factors to look for, what are the underlying properties of these queuing media, and like what I should be worried about. He specifically advocates this method called the use method. He looks for utilization, saturation, and errors. And you'll find that the metrics I like the most and that I advocate in this talk are the saturation metrics. RunQuue latency, the CPU starvation metric, is a saturation metric. It is how often was the CPU saturated and unable to serve. So this brings us to the other component of most processes' lifecycle, waiting voluntarily. There are all sorts of reasons why the scheduler might put a process to sleep voluntarily. So a process might accept waiting for a connection to come in, or receive, or wait for a timer by sleeping, or wait for a memory address to have some state with a few ticks, or wait for a process to exit with wait PID, all sorts of things. And then there's one last thing that we'll cover. A process can be put to sleep involuntarily by sending it a stop signal. That'll tell the scheduler, don't schedule this process anymore. So this brings us to a table of familiar process states. There is running, which I consider a misnomer. When I hear the word running, I think, oh, it has a CPU, it's running on a CPU. But really that means it's runnable. It doesn't mean that the scheduler has provided it a CPU. There's uninterruptible, which is code for waiting on a disk. There's interruptible, which is waiting on any of the other things we looked at. There's stopped, sent a signal to just stop. And there's zombie, which is waiting for a parent to call wait PID on it. And there's some gory details. We can look in include Linux sched.h for those. But that's about it. So now we can define load average. Load average is pretty simple once we understand process states. It's based on this idea of instantaneous load. How many processes, threads, tasks, whatever you want to call them, are either in the R state or the D state. Sum that up, and we have this thing we call instantaneous load. The scheduler samples this number every 5 seconds and accumulates it into an exponentially weighted moving average. So load 1 is a moving average with a 1-minute parameter, and load 15 is with a 15-minute parameter. And all of this is calculated in these and associated source code files if you're really interested. The calculation does get kind of hairy and annoying with multiprocessor systems. But it is actually that simple. It's just running plus disk. I don't like load average. Load average mixes together the properties of my disks and the properties of my CPU. And it's also sampled in a way that isn't as efficient as if I had just told something to read the runqueue latency every second. For CPU, I like looking at runqueue latency. For disk, I like looking at average queue size from IOSTAT, which we already covered. And I like looking at this other thing called delay account block IO ticks. Delay account block IO ticks will be pretty familiar now that we've covered CPU starvation metrics. And it's just disk starvation metrics. For how long was this thread or process or task put to sleep waiting for a disk? In this case, I ran git blame, and once it was done doing all the looking through my git tree, it took 19.68 seconds asleep waiting on the SSD to get its result. And we can graph this, like with Cassandra. And we can see that Cassandra doesn't spend all that much time waiting on a disk. It does, around 5 a.m., see a spike. But even still, these numbers are like, here's the 4%. That's the 4% line. It's pretty low. Like for a database system, this is not too much time waiting on disk. But I'll give you a grain of salt to take with these metrics. Many of them are workload dependent, and we have to keep in mind what that workload dependence means. So here's some pseudocode. It's not Python, even though it looks like Python. But what we have is a thread that reads from a random position on disk, and it does so in an infinite loop. And we're going to launch 500 of these threads. And just to give you an idea of our resources, we have 32 or more cores and one SSD with a maximum performance when there are 16 to 32 outstanding requests. So the question for the audience, which I won't make you answer, is what is our load average when this program is running? And the answer is 500. All of these threads will be either runnable or waiting on disk. So we are pretty sure that the load average will approach 500. And we also are, it's likely that most of them will be spending almost all their time waiting on disk. So we can expect delay account block IO ticks to rise at a rate of 500 seconds for every second we sample. Let's take a similar but different workload. This does the exact same random reads, but each thread, before it's allowed to do a random read, it has to wait for a semaphore. And the semaphore has 32 slots. So now a maximum of 32 threads can be reading at one time. Only 32 can be in the D state. Most of the threads are actually going to be waiting on the semaphore at any given moment if I sampled. So they're all going to be in the S state. We can expect about 32 threads in the D state and approximately 468 threads in the S state. And some threads will be in the runnable state in between, moving between S and D. Under this situation, the load average is going to look drastically different. Our load will max out at 32 or so. And our delay account block IO ticks will also rise at approximately 32 seconds for every second we sample. So this is the same workload. We are achieving the exact same thing. There's not much of a difference here. But what I'm pointing out is we have to be aware as we upgrade from one version of MySQL to the next that if the programmers did something like insert or take out a semaphore, that might explain the massive increase in load average we see or the massive increase in block IO delay we see, even though our workload hasn't changed and we are still serving our customers at the same rate. Just be aware of what the software under the hood is doing will give you a better idea of this. And if we look at PS, we can get a pretty good picture of it by going, oh, all these other 468 threads are in the S state. That explains it. So changes in workload will have effect on both bad metrics like load and good. And locks, like this semaphore here, are a form of queuing. Like semaphores under the hood just implement a queue. Most of them implement first come, first serve queues. Some of them implement priority-based queues. And typically bad ones implement randomized queues. But locks are a form of queuing that we should keep in mind as we analyze performance of our applications. And I imagine that won't be too surprising to MySQL people in here. So, questions? Nothing? Okay. So now we can move on to a simplified example with MySQL. MySQL will handle a query in a way somewhat like this one. A query packet arrives at the NIC. The kernel adds the packet to the socket queue, and that wakes up a receiving MySQL thread. So it moves from the S state to the R state. It was waiting on a socket, S, and now it's running. It's going to do a buffer pool lookup. In the process, it might wait on some locks. While it waits on those locks, it's going to move from the R state to the S state. When it gets the lock, it's going to move back to the R state. The buffer pool lookup was a miss, so we now need to read pages from disk. The reading from disk will move us into the D state, and once we're done, we'll come back into the R state. It's a big result. So as we send it to the client, we're going to fill up our TCP send buffer. And the only thing that will allow us to continue sending is the other side ACKing those results. As those ACKs come in, the OS will allow us to move back into the R state. And once we're done doing all of our sending, we can go to sleep and wait for the clients again. We'll just call the receive system call, moving us from the R state back into the interruptible sleep state. And then we're done. That's all we need to serve a MySQL query, right? There's nothing under the hood. That's just it, right? No. Simplified here is a keyword. Did the packet processing happen due to interrupt or due to polling? We don't know. Where the CPU cache is hot because we already had a MySQL thread on the CPU. We don't know any of these things. What we know is how the scheduler perceived our thread while it was handling a query. So latency analysis, which is what we're doing when we say, how long did it spend in the S state? How long did it spend in the R state? Is fractally complex. CPUs and CPU schedulers and everything else are abstractions that hide complexity. Is our CPU throttling? How many cycles did we stall for memory access? We don't know any of these things, but the key thing to keep in mind is we do it anyway. We say we spent 5 seconds of CPU time to handle these 10,000 queries. And we can make somewhat educated comparisons between two different MySQL threads or two different query workloads by just making some simplifying assumptions about the impact of a MySQL query on CPU time. So how can we collect latency information like how long did we spend waiting on disk I/O? Well, one of them would be timing, and another method would be sampling. Timing is almost ridiculously simple. You have some accumulator, big T, and you have current time, little t. So you take the end time minus the start time, and then you throw it into the accumulator. That's exactly what we saw with the runqueue latency or the delay account block I/O ticks on previous slides. This slide's good. It's about an optimization to make your timekeeping faster. I highly recommend you read it on the internet once the presentation's done. This brings us to sampling. Sampling with Little's law is this idea that in any stable system, that is one where the queue is not reaching off towards infinity, the number of dwelling customers in the system equals the arrival rate times the mean dwell time. And everything here is prefaced with the word mean. Little's law has to do with averages. So let's take an example. If we know that there are 1,000 MySQL query threads at play, then we can say that, I'm sorry, do I actually have 5 minutes left? Ma'am? Okay. It's a 25-minute presentation? Yeah, okay. If we have 1,000 query threads and we have 100,000 questions completed in that time frame, then we can use Little's law to say that we know on average it took 10 milliseconds per query. So over the same period, we can do some more analysis with Little's law. If the application saw 23 concurrent requests at any one time, but the MySQL only saw 10, then from the application's perspective, it took 23 milliseconds per query. We know that there are 13 milliseconds of unaccounted for time on average. We can then start searching for it. We can start timing how long does it take to parse the query result set, or how long does it take to format the request. But we have an idea of, MySQL thinks it's proceeding really fast. Maybe the network is taking up 4 of those milliseconds. But the problem with this is that it's an average. Little's law operates wonderfully irrespective of your distribution, but all it gives you is an average. We have an average about our queries in general, and that brings us to the question of why aren't we using histograms? Well, one answer is Little's law doesn't operate on histograms. It's not valid to divide percentiles in the same way Little's law can multiply and divide averages. And at every organization I'm familiar with, the number of time series that can be stored is a limiting factor. If I say, hey, I'd like to store 8 times as many time series, someone is going to get kind of unhappy with me. An average requires 2 counters to be sampled, plus 1 if you want to keep track of variance. A useful histogram requires 16 counters to 276. The 276 number is the maximum number of buckets that can be allocated by the Netflix speculator library. So we could track more as averages than we could ever track as histograms. Should we track histograms? Certainly. If someone says, hey, we need to know the API response time for this set of Cassandra queries, sure, track that as a histogram. We know that we have an SLA on that. But for everything else, like if I'm tracking the average number of context switches per Cassandra query, I think that's worthwhile for an average, and I'm not going to track that as a histogram. It's just too much information flowing too fast. So that brings us to the end of information on collecting about latency. Does anyone have questions on what we've covered so far? Okay. So we can now discuss a tale of 2 tenants. We have this service. It's the fishpicks service. The fishpick service has 2 major paths. It has a cache hit path and a cache miss path. Cache hits are really fast. They take 1 millisecond. Cache misses are slower. They take 100 to 10,000 milliseconds, 10 seconds. That's where the fishpick service has to go to an external provider of fish pictures and say, hey, I ran out. Could you give me some more fish pictures? So this brings us to our first answer to bad averages. For the fishpick service, we can track the cache hit time separately from the cache miss time. Instead of saying the average response time from the fishpick service was 5 milliseconds, we can say the average cache hit time was 1 millisecond with latency in the microseconds, or sorry, with variance in the microseconds. And we can say that the average cache miss time was 1,000 milliseconds with variance of 200 milliseconds. This gives us much more valuable and detailed information than tracking the aggregate ever could. And we can be careful to track the time waiting in a queue for a fishpicks service worker separately from the time that the fishpicks service worker actually did its work. By splitting one average, which might be how long did fishpicks take to respond, into 3, we can gain far more insight. But insight does nothing to fix the fact that fishpicks is multi-tenant. If misses get too slow, the hits, which could be served in 1 millisecond out of the cache, will have to wait for workers. They'll queue up. The hits which are so fast will queue up behind misses, which are so slow. And this double tenancy is not going to make our customers happy in like breakdown scenarios where maybe the external fishpicks provider is not serving as fast as maybe they once were. So we should get this notion of fairness into our heads. If a 100 millisecond RPC takes 3 milliseconds in a queue, then that's a 3% slowdown. That's like, okay, 3%, I was prepared to deal with that. If a 100 microsecond InnoDB key value lookup waits 3 milliseconds in a queue, then we should be like, wow, 3,000% slowdown. We have to care. We have to like alert someone. So we have this notion, we can formalize it. The author who I've seen who's formalized it is named Moore-Hockel-Balter. And she defines slowdown as queued time divided by working time. And I think it's especially worthwhile whenever a human's waiting. I always think about it in terms of the grocery store, where when I check out and I just want a candy bar, I'm really glad that there's an express lane available for me to go to. And so I don't have to get in a queue behind a family of 4 that's checking out with their week's worth of groceries. So in a databases concept, we might say we'd prefer to separate the queues for OLTP workloads, which should complete queries really fast, from batch workloads, which might take longer. Slowdown, I think, is a method of managing expectations. Here's where I first saw slowdown defined, is in this paper, task assignment with unknown duration. And this paper is awesome. It describes a really interesting algorithm quite lucidly and intersperses it with the queuing theoretic math to make it all work. This book is by the same author and does the same thing in discussing a great many more algorithms and teaching me and anyone else who peruses it a lot more about queuing theory. I have not read this cover to cover, but what I have read is quite interesting and I always learn something. So here's a page from the book. I think some sticklers might be angry with me if I didn't include a graph like this one in a presentation about queuing theory. Here we have the system load measured from 0 to 100%, and then the expected number of items in the queue for that system load. So it makes some assumptions about how jobs arrive and then depart from the system, and the number of processors in the system, which in this case is 1. But we can see, like, as the load approaches 1, that the number of jobs in the queue that you have to wait behind approaches infinity. But back to fish picks. So the fish pickers service has this problem where misses could block out hits. But what if we said that we will limit the number of workers that can be handling misses at any one time to 90% of the workers? If we have 100 workers, then 90 of them are allowed to handle misses. When the 91st miss happens, instead of going out and fetching a fish picture from the external provider, we just say, I'm sorry, we couldn't handle that. If we do that, we get to keep nice things like having a single load balanced pool of fish picks workers. But we have set a performance limit where misses can't block out hits to an extent greater than 90%. And I really like this because I've seen numerous examples where someone says, oh, well, let's set up one pool for the external API requests and another pool for the internal API requests. And that way the internal API requests could never block out the external ones. And then we have to maintain 2 different pools. We have to deploy to them separately. We have to load balance them separately. And we have to ensure that each one is correctly sized. With this method, we have 1 pool. I think it lowers the administrative overhead to just say, we have 1 pool, and when we're about to engage in this one activity above some threshold, like 90%, instead we'll just fail. This also means that you can over-provision. If you have 1 pool with 5 different tenants, then your overall service budget could be provisioned to 150% of your capacity. But each one of those tenants would be allowed no more than 30% of the operation. Under most scenarios, it's only 1 tenant that is really causing a problem at any one time, so you can get away with fewer servers without impacting your users. And now, I'll point out, all data stores are multi-tenant. And I don't mean this in too hyperbolic of a sense. Like, in any data store that's handling multiple query threads at a time, the performance of one query thread could be sacrificed to help the other. In most data stores that care about performance, they batch and coalesce work. So, like, InnoDB is not going to write a data page immediately as the data gets mutated. It will instead coalesce it and later flush it. Background threads are, of course, going to compete with our query threads. And lastly, most people do backups on their databases. Backups are background work too, and that could compete. So let's take an example. MySQL backups. And we'll say we're using extra backup here. Extra backup, a typical extra backup pipeline might be read, do some compression, and then send it over the wire. For that situation, reading is going to be disk bound. Compressing is going to be CPU bound. And sending will be network bound. For each one of these things, we wish to prevent the activity of backup from conflicting with query. So for reading from disk, we could say, why don't we use IONICE to put ourselves in this idle class? A read request to the disk will only be dispatched by the disk scheduler if there's no query request pending. Rather, a read request will only be scheduled if there's no other request pending. For compression, we'll do a similar trick. We'll say, hey, CPU scheduler, please only schedule my thread if there is no other task requesting CPU. Sending over network, there is the sole priority socket option. Using this, we can say, these packets aren't necessary. They don't need to be sent immediately. Please starve them if there's any other packets to be sent. And that way, if MySQL needs to get a result set back to the user pretty quickly, we don't have to worry about backup packets interfering. And note, we've picked no constants here. We didn't pick, oh, well, we'll allow the backups to use 40% of the network link. We'll say we'll allow them to use 100% of the network link when it's free and 0% when it's not. This technique is called classful scheduling. Work is divided into classes. If high-class work exists, low-class work has to wait. Nice is not classful. Nice still gives a nice process access to the CPU. It just gets access for a shorter time slice. And, of course, the backup process could starve. It might be that there's always that the disk is so loaded that it's just never going to run. But I feel way happier about that, and I can get my monitoring to tell me that on an hourly basis rather than query threads starving and needing to worry about it on the second. So I think that this is a very wonderful way to make it so that my backup's complete in a timely fashion, but without having to block query threads. Another example is Cassandra compaction. It's a similar background workload. It has to be done. It's actually a little more important that Cassandra compaction get done on a timely basis. The worry being, if you don't get your compaction done, your reads will get less and less efficient. But the options that Cassandra gives us to tune compaction are how fast should we allow each compaction thread to run, or how many threads should we operate. These are both all right things, but I don't like picking my rates a priori. When I get a faster CPU, I don't want to have to retune this rate. So just throwing all these threads into the idle scheduling class means that they might starve. So we might want to say we will instead guarantee that one compaction thread or two compaction threads will always be able to operate and that they won't interfere with our query threads. So a solution for this is the Linux CPU sets facility. CPU set means that we don't have that we separate which CPUs the compaction threads are allowed to use from the CPUs that the query threads are allowed to use. If this is interesting to you, I highly recommend this paper called HERACLES. HERACLES was Google saying, well, we really want to run both search spidering and like search key value lookups on the same machine. Spidering is a batch workload, and key value lookups are latency critical. Can we do this? And they said, oh yeah, certainly. They put them together, and they went resource by resource saying, well, how could they conflict? Will the machine get too hot as a result of this one and cause these CPUs to throttle? Will caches get will the level 3 caches in the CPU be affected by the activity of this process in a way that is to the detriment of that process? So there's all sorts of fun ways to manage multi-tenancy. One of them that I haven't covered and many people are a big fan of is token buckets. Token buckets are a method of limiting the rate of a given activity. There are C groups. One C group that we just mentioned was CPU set. And on Linux, there's queuing disciplines. These are scheduling when network packets hit the network. One of the most fun, I think, is Codel. It's the second most interesting algorithm in this talk, and we're not going to discuss it at all. I'm sorry. So we're three-quarters of the way through. Does anyone have questions? Okay. So this brings us to the last section of the talk. And I'm actually kind of surprised we made it here. Load balancing is how requests are allocated to backends. The ideal thing to do in load balancing would be to have a central queue from which all of our workers can pull from when they decide that they're ready for another request. And this would minimize queued time under some unrealistic assumptions about how job sizes vary and how they arrive. But in like practical applications, actually having a central queue of your jobs is a very good method for load balancing. So what are some very bad methods? Well, random is pretty bad. If we just randomly choose a backend for a given incoming request, then if we have, let's say we have this sort of arrival process where events come in periodically, and we have not much of a way of guaranteeing when events will arrive. Random will ensure essentially that requests stack up on some queues and other queues sit empty. Round robin is slightly better. It equally allocates requests across queues, and it spaces out requests. So we know. So if a server got this request here, it's not going to get this next request. So it does space out the distribution of arrivals a little. What's better? There's join shortest queue. If you use HAProxy, this is called least cons. If you use Nginx, it's called least_con. This is the idea of, well, if one server has 6 outstanding requests and another one has 5, we'll send it to the 5. But we have no clue whether the 6 outstanding requests are really intensive, like tough requests for that server to handle, or whether they're fluff. In other words, we have no idea. We're making an assumption here that jobs are equal size, when in fact that's not the case. Most web requests or database queries or all sorts of things have orders of magnitude difference between the smallest request and the largest. And for workloads like that one, we can look at this novel algorithm called tags. Tags, unfortunately, is not practical in that you can like go out and get a piece of software that implements it. But I think it's amazingly instructive when learning queuing theory. So, to prepare your mind, tags is a system that intentionally throws away work, intentionally unbalances load, and prioritizes fairness over throughput. I think the first two are pretty controversial, and the last one's like, yeah, actually fairness is good. So, tags is what we call a work non-conserving scheduler. It throws away work and it leaves resources idle when they could otherwise be loaded. The opposite would be a work conserving scheduler. Like the Linux CPU scheduler is a work conserving scheduler. The CFQ disk scheduler actually has some non-conserving components. So what are the key concepts that motivate tags? Well, one of them is that jobs are non-preemptible. That is, once we've started a job, we have to either run it to completion or kill it. We can't stop it halfway through and expect to resume. They are idempotent. If we run a job, kill it, we are allowed to restart it from scratch. There's a large variance in job size over maybe 3 orders of magnitude or more. And because of this variance and our unwillingness or inability to make predictions, we have to just deal with incoming jobs as they come. I think this is pretty realistic. In most cases, it's not, you do have workloads where you don't know if something's going to be a cache hit or a cache miss a priori. Finally, we have we are judging ourselves against a slowdown metric. This is the slowdown metric we were discussing earlier of the amount of time I spent in queue waiting for my candy bar should be divided by the total amount of work I'm presenting to that system. So one candy bar should entail less queuing than a grocery basket that is chock full of groceries. Finally, we're going to use this requirement metric, which is server expansion. So if I say that I have a given incoming rate of work, the server expansion requirement is how many servers do I need to add to my system in order to get myself beneath a certain slowdown metric. So if I say I've got 5,000 CPU seconds of incoming work every minute, how many CPUs do I have to add in order to get beneath 20% slowdown? Well, tags is in many ways optimal for such a situation. This is the tags algorithm. Arrivals come in and get queued on host 1. On host 1, a job is only allowed to run for a very short period of time. If it completes, that's great, we're done. Exit the system. If it doesn't, it gets killed, losing all of its progress, and gets re-queued on host 2, where it will be allowed to execute for a little longer. And there's a whole set of equations for calculating what the constants are at each host in the system. What this means is that jobs that require very little of their time will spend very little time in queues. And as jobs indicate by test that they do require more time, they will spend more and more time waiting on queues. So here's an illustration of what the tags load balancing algorithm will look like. We see at system load equals 0.5, that means the overall system has twice as many compute resources as is needed to handle all of the incoming requests. The load at host 1 down here actually drops to near 0 for highly variable job distributions. And host 2 takes up most of the work. So for these highly variable jobs, we achieve a lot of worthwhile effort with this very unloaded system just by getting the really quick jobs out of the way really fast. And then we shunt all the longer jobs over to host 2. If we move over on this end of the graph, this is where jobs are a little less dispersed. The distribution's a little more compact, and we see that we're not having as much of a load unbalancing effect. And then finally, I'm terribly sorry to the audience, but this gray line is hard to see. This is the sum of loads. So here we see that tags is very efficient. It doesn't throw away too much effort for highly dispersed job distributions. But we throw away a little more as the distribution becomes a little more compact. And with that, we have 3 minutes left for some final questions. Anyone? What's up?
Are there any distributed systems that you know of that have implemented tags as the default routing?
No. I've always said that the best use of tags would be on like a distributed build cluster, where some builds need to run like 4 tests in a massive test suite, and we should get those out of the way quick. And other jobs will like take hours or days. And for each case, like a day-long job might be willing to sacrifice 30 minutes in a queue, but we want to get that four test run out of the way. Cool. Well, thank you.